Welcome back to BioInsights. This is a show where we connect the exercise science to the real world application for the facility operators, coaches, clinicians, and the athletes that they serve. Today's conversation, I want to set the frame actually before we kind of dive in. An athlete or anyone that's going to a gym grabs a barbell, 500 pounds, let's say, stands and pulls it off the floor and holds it there at the top lockout position of a deadlift for about 10 seconds. So some people will relate to this. It's maximum effort. Muscles will shake. Their muscles are shaking. Heart's pumping. They're stressing. You could see the stress on their face, and their nervous system's completely fired. So been having this conversation with Dr. Juris and other professionals in the industry. And according to these laws of physics, because the barbell didn't travel and it was at the furthest lockout point, he's basically or she's basically performing zero mechanical work, exactly zero, which sounds completely absurd to anyone that's ever picked up a heavy weight. But mathematically, it's undeniable. It's true. So the paradox today about this episode is going to cover three things. One is we're going to challenge the way that the industry is measuring training sets and reps, and not the physics equation. It never was there. Was there a better framework? And kind of what kicked this off too was recent ACSM publications of new perspectives that we just both chuckled at. Secondly, we're gonna talk about the case for training on one leg at a time, and not as a variation, but as a primary model. And then lastly is we're going to take apart the lunge, and we're going to just use that as an example of talking about rigid body, joint by joint, force vectors, and what certain concepts that are being taught does to actually your knee if you repeat doing it. So joining me for the fourth time, our resident, Dr. Paul Juris.
It's a residence already, huh?
Yeah. You pretty much you've already achieved it, along with the NBA, PGA, NFL consulting services that you've done, and all the other work history, side
I've cracked
bets.
the code.
Yeah. So welcome back.
Thank you so much. Um, yeah, I mean, standing there with, anybody walking in a gym who can lift 500 pounds and stand there with them, more power to you. That's quite the feat.
I think the industry right now is realizing that um, it's an ongoing repeatable problem that we keep seeing these concepts and these frameworks of effort, right? And it's not the athlete, and it's really what we're trying to measure. And I think I refer to tracking sets and reps is like tracking how many times you're asking whether you drove up a mountain or coasted downhill. The rotation of it basically of that wheel tells you the actual work being done, but it's still missing a gap. And that's where I feel like sometimes when people are looking at sets and reps, they need to understand like it doesn't account for um, the rest of what's really the goal of getting out of mechanical work.
So, you referenced the ACSM guidelines,
Yeah.
which just came out, and there was a lot of hoopla around that because it's the first time that they've published these guidelines in, I don't know, a decade, whatever the case is, and they had all of the different elements of training for strength, whether it's load and rest intervals and sets and repetitions and volume and all of these things. And it was like earth-shattering that they've identified the key variables that will make you stronger. And it's like, what a finding. And I'm looking at it thinking, wait a minute, like this is stuff that we've been talking about for 40 years. Like, what do you mean it's earth-shattering? It's the same stuff regurgitated, to your point. And when I look at it, I don't look at these individual values or variables and say, "Ooh, I want that one or that one." What I do is I look at it and think, how do these interact? What are the different things that I could pull together that would allow me to measure something that's going on? And in terms of, sets and reps, I've been working with tech companies for a while, and the first thing they say is, we're going to count reps. And I'm like, okay, go ahead. I mean, I don't need somebody to count reps for me. I don't need a piece of technology to count reps for me. I can do that in my head. Like, there's nothing that I need to spend money on, particularly a subscription-based thing, so that all it's going to tell me is how many reps I did. It's just nonsensical. So the one thing, though, when you start to look at the different variables that they indicate are critical, load, okay, definitely, volume, sure, range of motion, okay, those things we need. You start putting all of these things together, what you end up with is work. And you mentioned it, mechanical work. That's what we should be measuring. How much work does somebody do? And instead of creating workouts where we're doing X weight for X number of sets with X number of repetitions with this kind of rest in between, you just say, here's how many joules of work we're going to do. And I don't care how you get there, just do the work. And ultimately, when you start to do that, you'll get workouts that are really meaningful, because then you can vary the work, you can vary the work targets, you can use different speeds, loads, anything you want. You can still get to the same work objectives.
So if hour is work divided by time, and if a trainer measures that with a client and that's producing more watts at the same submaximal load week over week, what's that telling them that a rep could never count?
So, all right, so you added another element. So let's understand what work is first of all, so that we can really dig into this a little bit. Work is force times distance. So now, in putting that in the context of these variables that the ACSM has just highlighted, load is going to determine how much force I applied depending on how fast I want to move that load, right? So the more I want to accelerate a load, the more force that I have to apply to it. The heavier that load gets, the harder it is to accelerate. That means I have to apply even more force. So load has a direct impact on force. And distance is the number of reps you do, but it's also the range of motion that you do within a rep. So I could put a huge load on, like you mentioned, 500 pounds. I could hold 500 pounds, but if I'm only moving it an inch, I'm not doing that much work. You even said if I'm just standing there holding it, and by the way, my hands or my wrist muscles and our forearm flexors are screaming, my shoulders are screaming, I'm shaking. Yeah, but I'm not doing any work because the bar's not going anywhere. Now, am I expending energy? Yes, but I'm not doing work. So range of motion will determine distance, right? So the greater the range of motion through which I move, both concentrically and eccentrically, the greater the distance that I'm moving this load. So if I track force and distance together, I get work. If I divide that by the time it took me to move that weight that distance, producing the force that it needed to do it, then I get power. So power is just the rate of doing work. And if I have the tools to measure this stuff, then it becomes super valuable. And what I want to do is I want to see, how does my work change over time with a given load? And what are the variables that are causing it to change? Am I accelerating it more? Am I moving it farther? Those are the kinds of things that I want to look at that tell me what kind of quality workout I'm achieving.
Based on some of our prior conversations, we talked about neural drive and the force velocity curve, and we talked about intent. Um, in this regard, right? What if the intent was to move always as fast as possible all the time, right? We're telling our client to always the intent is to move this as fast as you can, but they produce more watts at the same time with that same submaximal load week over week. Um, but I know they did 3 sets of 8 or 3 sets of 10. What Obviously you can't see what the peak wattage and and what the other movement data that we're describing here more effectively than 3 sets of 8. And I think that's the old framework that they're just defaulting to. And I think that we can, with us, we've been talking about this for years, and it's not that it's actually fails to view what could be possible today because let's take that same scenario. Every trainer's faced it. An athlete comes in, they're fatigued, sleep deprived, their nervous system's fried, but the program says 3 sets of 10 at 80%. And so how do we adjust to hit the right mechanical dose without grinding the athlete into the ground? And I think that's another thing that today we can see that we can work on some of these attributes. We can look at peak velocity, we can look at power, we can look at eccentric phases of movement, we can look at the concentric. So we have that capability, and I think that's where this work-based framework, um, we need to explain that a little bit more. I think there's a gap there with that they're missing and not really talking about.
It's an interesting question because we're using these simple metrics to say, okay, well, did you do 3 sets of 10 at 75, 80%? Did you do it? And if you did it, then great, we're making progress. But what we're not necessarily looking at is how well did you do it, right? What if you're accelerating a weight? And I like to use acceleration. I mean, velocity is very valuable, but I like to look at acceleration. It's
Can,
also part of the force
can you
equation.
define
It's part
both?
of, pardon me?
Can you define velocity and then acceleration so people have a good understanding? Because everyone says, well, isn't that the same? But
Yeah, yeah, sure. So there are three kinematic variables that we're looking at. Kinematic meaning motion, right? So there's displacement. Displacement is change in position, right? So from start to end, it's change in position. And it's nuance, right? Because if I'm running around a track, if I have a 400-meter track and I run around the track and I go from the start and the end is at the start, my technical displacement is zero because I ended where I started. So a change in position, um, it gets a little bit nuanced there, but just let's assume a displacement is change in position. Velocity is rate of change in position. How long did it take me to change that position? Now, inherent in velocity is direction. So people confuse speed and velocity. Speed is just, it's a scalar, it's an absolute, it's just how fast. Velocity is how fast in what direction. So it's a vector quantity. So velocity is rate of change of position towards a specific direction. And acceleration is where people get a little confused, right? So acceleration is change in velocity over time or rate of change of velocity. So if I have a weight, it's on the ground, its velocity is zero, and I have to lift it, I have to accelerate it. That's what I'm doing. I'm accelerating that object. And I do it by applying force to the object. I'm either going to pull it or I'm going to push it. That's force, by the way. Force is a push or a pull. So I'm going to pull it or I'm going to push it, and I have to accelerate it. So the acceleration is how rapidly is the velocity of that object changing, right? It's going from 0 meters per second to, let's say, 3 meters per second. How long did it take to go from 0 to 3? That's acceleration. Now, the interesting part about acceleration is it's positive and negative. So velocity can increase or velocity can decrease. So I can't have a negative velocity. My minimum velocity, the basement for velocity is 0, but I can have negative acceleration, and this is what throws people into conniptions. But negative acceleration basically is deceleration. So it's how rapidly is velocity, or how quickly does velocity slow down? So as it's slowing, how long does it take to slow? And that's negative acceleration.
And, you know, for people who haven't heard our prior discussion, we talked about kinetic chain and energy leaks. And this kind of was also part of our velocity-based training, where we talked about driving with intent, as well as metrics that I help identify specific training outcomes. And then we talked about a little bit about is the body asymmetrical, and we talked about bilateral training, and we wanted to really have a better understanding of bilateral training compared to unilateral training. And I think there's a great opportunity to kind of talk about a subject that you've done a whole extensive program on, which was lunging. And as it sets up really the concept of how we move, and we were talking about how this can actually progress and into fields that I feel like we're starting to see more unilateral training, but I feel like realistically, you don't need to be under the bar all the time, especially if you're or at a specific age. So can you kind of give us some insight on your concepts of unilateral training compared to bilateral training?
Yeah, I mean, I think they're both valuable, but I think unilateral training offers us a lot of opportunity to change the constraints of an exercise in a way that adds multiple elements to it. What's interesting is I was just flipping through some videos, and I saw an interview with Mikaela Shiffrin. So Mikaela Shiffrin, if you don't know who she is, she's an American skier. She just won her 6th overall World Cup title. I mean, she's an amazing skier. And I've been skiing for my entire life, so it's meaningful to me. And she was talking about her training routine, and she said, I only do unilateral training. And I thought, wow, because here's an activity, ski racing,
Yeah.
where both skis are on the ground at the same time. I mean, unless you're taking air, let's leave that aside for a moment. But turning through gates, those skis are working together, and they're both on the ground. But the thing about skiing is you're applying more force to the outside ski when you're making a turn than the inside ski. So there's this force distribution, this constant changeover from one side to the other side, which really speaks to why someone who's doing that kind of a sport should be considering unilateral training. Unilateral training has a lot of benefits. And what's really interesting, if we get into the nervous system part, and Marcella, you're aware of this, there are a lot of terms for this. Cross education, right? Right.
The other one.
Efference copy, right? Some of those terms, really what it means is that when you develop force on one side, when the motor cortex sends a signal
Yeah.
down one side, and by the way, they cross, right? So if you're moving your right arm, it's your left motor cortex that's controlling it. So corollary discharge is another word for this. when the left motor cortex sends a signal to the right arm, it sends a copy of that signal
Yeah.
down the left side. And so there's this cross education concept. So, it's interesting because research has shown that if you only do strength training with one side, let's say your right side, your left side is also going to get stronger because the signal is going down the left side. Now, let's be honest, you don't get as strong as the side you're training, but there is a change.
It's the neurological pattern that does. So you
That's
don't have
right.
the same cross-sectional muscle fiber as the other appendage, but the neural drive is there for it. So it's just training to develop more muscle density.
So what it also does is when you send this kind of ghost signal down the other side, because the other side's not lifting anything, right? The
Yeah.
other side's not really doing anything. But what you're doing is you're sort of stimulating and teasing the synapses, which will then ultimately prepare them to fire effectively when they're called upon to fire. So what they're doing is they're sort of preconditioning everything on that side to be able to work more effectively. So there is a benefit to unilateral training from a neurological perspective. The other thing that is really helpful is if you have a bilateral deficit, then training unilaterally allows you to manage the work that you're doing on the, let's say I call it the involved side, the weaker side, the injured side, whatever that may be. You can manage the work output so that you can try to normalize the differences between them. Now, I said on in our last conversation, we're asymmetrical beings. Like humans are not perfectly symmetrical. So always one side's going to be stronger than the other side, but you can make up the gap. So when I was rehabbing ACL patients, and this is post-surgery, when their involved leg was 50% weaker than their uninvolved leg, now you've got a huge strength deficit. How did I make up the difference? Well, I increased the work on the involved side. So we did 2, 3 times as much work on the involved side as the uninvolved side, but we always trained the uninvolved side unilaterally because of that cross education effect. So that's one element. Now there's more if you want to get into more.
I think the cross education side and the bilateral deficit alone, that those two reasons to be doing more unilateral work speak for itself. But then at the same time, most activities have you always on one leg if you're trying to get anywhere. So if you're walking, running, cutting, climbing stairs, you're moving on a single leg. So, I look at it this as the facility owners on floors are dominated right now by bilateral machines and bilateral programming, and so the motor patterns for members really specifically they're not building this purposefully, right? There's still a gap. And I think that's one thing that I'm seeing different, and is kind of a renaissance almost like up to the functional training realm, right? That term, which is cliche and inappropriate to use, but because what is functional training, right?
Well,
Um,
that's a whole nother topic of conversation.
yeah, and I just think that to kind of address this bilateral issue, I think a great training tool, and you've brought this up, which was asymmetrical loading,
Mm-hmm.
bridge to offset this, and it's the foundations are really with unilateral training. Um, so I think it's great to kind of maybe, you know, I guess frame it with an analogy, right? An asymmetrical load is learning to carry, let's say, a full tray as a server. At the gym, taught us to, carry equal load, right? Each in one hand. The real world really doesn't give it to you always that way. So there's going to be a spill, and that's how the body's going to compensate. And but that also helps address bilateral deficits. It also helps cross education. It helps address how the body really moves in the real world. So I think my point is if it's not just single-legged work, it's putting your body into positions of movement and creating force. And that's where we never ask the body to manage that effectively in an environment that's supposed to be helping the outside environment. What's your thoughts on what I just kind of framed?
Well, certainly there are a lot of moving conditions, when we're talking about the legs, whereby there are what I call unbalanced torques or unbalanced moments acting on the joints. And unbalanced doesn't mean we're falling over. Unbalanced means that the loading around a joint is unequal, right? So that is what makes a joint rotate, by the way. So what we can do with unilateral training in the limbs, and this is, we'll get into asymmetrical loading in a minute because it's a really fascinating topic. If let's say we're doing a unilateral squat, right? What the system has to do is it not only has to deal with accelerating the body's center of mass vertically when you're, let's say, moving from the lower position to the standing position, but it also has to deal with deviations in the center of mass in the frontal plane, so across the body. That's going to involve different types of control structures around the foot and ankle and the hip. Knee, not so much, a little bit, but certainly rotational aspects, inversion, eversion at the foot. So there's a bunch of stuff that has to be controlled. Now, on top of that, what if I want to add a load? There are different ways that I could add a load. I could put a load on a bar and I can do a unilateral step up with a barbell. That's one way to do it. Now, if we use equal weights on both sides, the center of mass of that weight of the barbell and the plates is like right where it's making contact with your body. So it's kind of a uniform load through the axis. But if I use a dumbbell, now all of a sudden I'm changing that weight distribution. I'm moving my center of mass around. So if I hold the dumbbell in my my ipsilateral side, which would be the same side as the working leg, that's going to stabilize that leg. But what if I hold the dumbbell on the opposite side, the contralateral side? Now all of a sudden I'm moving mass away from the base of support, which is going to challenge the muscles that control for adduction and abduction at the hip and inversion, eversion at the foot. So that becomes a different task. So what trainers or sports coaches can think about is not necessarily what kind of wacky exercises can I do to make this person better, but how can I use the tools that are around me, like kettlebells or dumbbells or plates or whatever they can find, to change the loading conditions and the characteristics of the movement so that we have to control the center of mass differently.
Brilliantly said. The force vectors that you described and the kinetic chain, and how people only look at joints sometimes as something as simple as a hinge joint. There is rotation, and the job of certain movements is to maintain that efficiency of movement that we described last time. So if for a client that's doing that single-legged or mobility work, how do we use asymmetrical loading in a bilateral squat pattern as a bridge?
Okay, so that's there's some research there. Interestingly, for all of the potential benefit that we can get from something like this, there have been very, very few studies done on it, which is really interesting. To my knowledge, there are only 5 studies that have been done in like the last 20 years on asymmetrical loading, which is fascinating to me. By the way, just before I answer that, I was thinking about this with the modalities and things. A lot of trainers and strength coaches, when they think about creating stability around the joints, the first thing they want to do is put you on a labile surface, right? An RX pad, a BOSU. It's like, no, that's not what we're talking about here. Because, and even like if you look at the new ACSM guidelines, curiously enough, they show that working out on unstable surfaces is no better than not working out at all, which is really that's a shocker to me. No, it's not. I mean, we've known that all along.
Yeah.
So, but the
It looks cool
idea,
on Instagram, though.
it's true.
Yeah.
We we understand that if we use the tools correctly, we can create these biomechanical constraints that force the system to behave differently. So now let's get to asymmetrical loading. And you mentioned it in terms of lower body exercise. So the interesting part about it is the studies that have looked at things like squatting, what they do is they give you a bar, but they put two different loads on the bar, right? So, and then most of these studies show that, yeah, there are some strength gains, but they're really no better than if you just do a symmetrical load on the bar. But here's where the studies are faulty. If I put a 45-pound plate on one side and a 25-pound plate on the other side, now I've got this unbalanced load on my spine. What do you think I'm going to do before I start my squat? I'm going to shift so
Yeah.
that I move the heavier load closer to my center, right? I'm just going to compensate. And you see this over and over and over again. And it's the same thing with an upper extremity, like a bench press. If you asymmetrically load the bench, what you will see is before the person starts doing the movement, they're going to shift the bar laterally in order to achieve equilibrium. So yeah, naturally, you're not going to see a difference in strength gain between that condition and a standard symmetrical condition because the user's creating symmetry before they start. Hence, now you bring in dumbbells. So to me, and what's shocking to me is I've seen no asymmetrical loading studies that use dumbbells, which is like,
That's
wait
the
a minute,
easiest
that's
way to
your
load.
obvious choice of
Yeah.
implement,
Yeah.
right?
Yeah. It's the easiest way to
So
load. I don't get that.
I don't get it either. So you hold a 40-pound dumbbell in one hand and a 10-pound dumbbell in the other hand, and now let's see what happens. And you don't compensate, and now the system has to deal with this unequilibrium type of condition that it has to solve for. It really works well with the upper body. And again, there's another nervous system component here. So going back to biomechanics and laws of nature, Newton's second law of motion is a law of acceleration, right? So acceleration is directly proportional to the force that you create and inversely proportional to the mass. As the mass gets heavier, unless you increase the force output, your acceleration drops. So now imagine this. You're going to do an overhead press, dumbbell military press. And in one hand, you got a 30-pound weight, in the other hand, you got a 10-pound weight. Based on the law of acceleration, if I'm pushing those things equally, the lightweight's going to get to the top first because it's lighter. I'm going to accelerate it at a higher rate. It's going to get to the top first, and then the heavier weight will get up there. Is that what happens? No, they both get there at the same time. So, and if people don't believe it, they can try it.
Yeah.
And what it says is that the nervous system, so what the nervous system wants to do is manage the overall degrees of freedom. What the nervous system wants to do is simplify the process. So the easiest thing to do is to make sure that both weights get to the end point at the same time. So what it does is it produces far less force on the heavier side and a little bit more force on the lighter side so that it can balance the rate, the velocity, and get these things to the endpoint at the exact same time. So that's what asymmetrical loading is doing essentially, is it's forcing the nervous system to control force output and make sure that the targeted movement is simplified. Where the benefit comes in is not in doing that. It's when you switch. So the first time you do an asymmetrical load, you're saying, ooh, that's weird. But then you figure it out and it's like it becomes normal. So now in the next set, switch them. So the heavier weight goes to the light, that what was the lighter side, the lighter weight goes to the heavier side. Now do it, and all of a sudden your brain's confused. It's like, what the heck just happened? That's what stimulates strength gains. That switch right there is what gets the adaptation going within the nervous system, and that's what promotes strength. None of the studies that I've seen in asymmetrical loading has done anything like that. Nothing.
Does that learning transfer to the unloaded real world movement though? How does
Yeah,
that?
you get stronger. So if you measure strength, if you look at construct validity means that you're measuring an outcome in a modality that's different from the one you were training, right? So if I'm doing asymmetrical loading, does it improve my ability to do push-ups or something like that? That's a construct validity. And the answer is yes. So like you get stronger overall when you do asymmetrical loading. Now, contrary to what some people think, asymmetrical loading by itself is not going to make up bilateral deficits. Like you have to do more work on the weaker side in order to really get it going, because during asymmetrical loading, the system always favors the stronger side. So if it's always favoring the stronger side, then you're not necessarily going to make up a deficit. So you have to do that a little bit differently.
And that weaker side, right? The dosing wise, it's not significantly much more, right? We're talking about 2 to maybe 3 more sets at most if you're going to address bilateral deficits.
Yeah, I mean, on that respect, when I was working with ACL patients, we would do like, if we're still thinking about it in the context of sets and not measuring work, we
Sorry.
would do three sets on the uninvolved side. I would do 10 sets on the involved side.
Yeah, so that work variable peak power would be sufficient, correct?
Absolutely. Work and power. And if you have the tools to measure those things, then absolutely use them, because those are the variables that you really want to be focused on. And like one more thing that I think is worth considering with asymmetrical loading, and this is similar to the concept of holding a dumbbell in different hands when you're doing, let's say, a lunge. You're laying on a bench, you're doing a dumbbell bench press, and in one hand you put a 30, in the other hand you put a 5. Okay, not only do you have this challenge of accelerating these weights, but now what you've done is you've created a huge torque around your spine. And so if you're thinking about how to engage core stabilizing muscles without, now this gets back to our earlier conversation about efficiency. I don't want to tell somebody to contract their core, right? That's not what I'm going to do. But what I'm going to do is design or conceive of an exercise which forces the central nervous system to factor core contraction in. And I can do that with an asymmetrical load, because you got a heavier side, on your right side. It wants to rotate you off the bench. So you have to stabilize against that rotation. And that's what some of these upper body asymmetrical loading studies are showing, is when you do it, you're getting core contractility in order to stabilize against the moments that are created by that offset load.
My favorite asymmetrical play around for me is on the bench or a farmer's walk.
Sure.
And the farmer's walk is a hell of I'll have a 75 pounder in my left and then a 50 in my right, or a 30, depending upon how what I want to target. And I find that window is really ideal. It doesn't have to be significant. It could be a bigger window, like a 40-pound variance or a 20-pound variance. But to your point, the goal is when you shift it and you challenge it again and going, wait, this was heavier last time. That feeling, that sensation is a big, big difference.
Yeah, and you mentioned the differential, right? So some of the studies, when they look at differential, it's like 5 pounds. Well, 5 pounds is not enough.
Yeah.
When you look at 5 pounds distributed across the sides, I mean, it's not enough to move your center of mass. It's not enough to really to challenge force production through this. It's got to be like it's got to be a 2-to-1 ratio if for it to really work. And by the way, if you want to do like a really real world situation for training, do that farmer's carry with a 75-pound dumbbell in one hand and your dog pulling on a leash on the other hand. And there you go. There's a real world situation.
Or carry all the groceries that you bought in one trip.
While you're talking on the phone. Yeah,
Yeah.
absolutely. There you go.
Yeah.
That'll do it.
We in our prior talk we were talking about the kinetic chain, and we talked we brought up the lunge.
Mm-hmm.
So the sequence, the joint events that take place in an ankle, the hip, and the knee, um, ankle, knee, hip. I mean, let's have it in order, right?
Mm-hmm.
What's happening at each, and what's the order? So if there's a trainer listening or a coach and wants to teach a lunge, um, what's that ideal sequence, and what have you been seeing in the industry that you feel like needs to die?
Well, yeah, I love the lunge because the lunge is such a dynamic motion. What a lunge does is it trains change in direction. I mean, that's what lunges do, right? So it's acceleration, deceleration, reacceleration. I mean, there are a lot of components to a lunge, and depending on how you do them, whether they're regular forward lunges, reverse lunges are done really poorly. So we could talk about that. Like most people actually lunge onto their back foot, which is not recommended because of the stress put on the Achilles. I mean, that's just it. I'm surprised people don't snap that tendon more frequently when they do that. Um, walking lunges, crossover lunges, anterior lateral lunges, leaping lunges. I mean, there are a lot of different lunges that you can do. But really, the traditional starting point is just the simple forward lunge. And the the thing that should die is the 90-90. That's what should die is keeping your knee over your ankle and keeping your trunk upright. That should go away as quickly as possible because it was the worst coaching advice biomechanically that I think I've pretty much seen in any exercise that I've ever observed.
It's the 220 minus your age,
That's right.
basically equivalent.
Yeah, it is. So the basic the key to doing a lunge well, and we talked about this with efficiency. The key to doing a lunge well is positioning your center of mass so that it can move efficiently through space. Right? I'm not sure that anybody has ever thought, other than people who have taken lunge courses with me, I don't know that anyone's thought of it that way. Right? But the purpose of doing the lunge, other than the power that you're developing, the goal of the movement from the front lowered position is to accelerate the center of mass smoothly and efficiently back to the standing position. All right. So now the vector that the center of mass has to travel is going to be backing up. In order to do that, I need to push forward and down and forward into the ground. This is Newton's third law of motion, right? For every action, there's an equal and opposite reaction. So in order for me to move my center of gravity backing up, I need to push forward and down. Now, there's a little phenomenon that is basically called distortion. And the best way that I can describe it is through thinking about billiards, right? So pool. I'm going to strike the cue ball and the cue ball is going to hit another ball. Now, if the cue ball hits that other ball directly in the center of the ball, that second ball will travel in the exact same direction that the cue ball was going. But if the cue ball strikes that second ball off center, so it's not through the ball's center of mass, that other ball is either going to go left or right, but it's not going straight. That's distortion. So when you think about doing a forward lunge, moving back to the starting position, when you apply force into the ground, you want the reactive force vector. That's the thing that's moving you backwards, the reactive force. You want that to go straight through your center of mass. And then your center of mass will travel in the direction of that force vector. The problem is when you do a 90-90, your center of mass is now positioned back and down so that when you create that force, it goes above the center of mass and it pushes the center of mass back and downward toward the ground, and hence all your weight ends up on your back leg. So when you push, and you could see people doing this when they do a lunge, they start pushing, their weight ends up on their back foot, and then they have to pull themselves back to the starting position using their back leg. Highly inefficient way to move, puts tremendous stress on the back knee, 87% more patellofemoral load on the back knee than on the front knee, and it's just a really bad exercise. So what you want to do is you want to shift the center of mass forward. You want to get your weight over the instep of your lead foot. You want to lean the trunk forward so that when you push down and forward into the ground, it pops you right back up to the starting position because that force vector is going right through your center of mass. It's putting you right back where you started.
And the limiting factors here sometimes could be what along one of these cue balls, right? One of these pool balls, I should say. If there's a range of motion issue, most likely typically in ankles, right? Limited dorsiflexion, limited plantar flexion, either or. It'll change that force vector. It'll create a movement leak, right, or in that kinetic chain, and we'll see potential risk of injury or overuse injury, potentially wear and tear, unnecessary wear and tear because the movement's not efficient.
Yeah, absolutely. I mean, it's if anything, it will make it less efficient. And then as movements become less and less efficient or more inefficient, that's when we start to put ourselves at risk because we have to compensate for those inefficiencies. So we start doing odd things. Now, we can get into a whole conversation around open and closed kinetic chain. And I know this is kind of hair raising for a lot of people because I've had this conversation with a lot of folks. But a lunge, a squat, all those things, those are open chain. So I know I'm going to get hate mail for this one, but hate email as it may be, or on my Instagram. But no, this is so technically a lunge and a squat is an open chain. Closed chain means both ends of the linkage model are fixed, both ends, right? And when you're in a lunge or a squat, only one end of the linkage model is fixed. The rest is free to vary. So you have, when you have a limitation in the ankle, when you're doing a lunge, you have lots of degrees of freedom all through the chain for the body to figure out how it's going to compensate for that. Now, it doesn't mean the compensation is always beneficial, right? Sometimes it works really well, right? Sometimes this is how people solve movement problems, by figuring out which degrees of freedom they can use to overcome deficits somewhere else in the system. But in some cases, those compensatory strategies actually lead to problems, overuse, too much stress, which can produce strain, things like that. So this is where we as practitioners have to look at people and say, well, how are they compensating? Why are they compensating? Is it helping them achieve their goal in an efficient way, or is it potentially causing issues that we need to address?
So let's give an example. So if we know the quadricep works eccentrically on the descent, for a trainer whose client's constantly always complaining of knee pain during a lunge, what's the eccentric load doing to the patellofemoral joint? And what does that tell us about how the movement was set up?
So it depends on the joint angle, right? So there are two factors which create patellofemoral compression. There's how much force is being applied across the patellar tendon, driving the patellar downward, but there's also what is the angle of the knee joint. So the highest patellofemoral compression usually occurs at about 60 degrees of flexion. That's when you see the most compression in the joint, whether it's concentric or eccentric. Eccentrically, we're just more efficient. We could produce more force eccentrically. So when we're going eccentrically, at that joint angle, it's going to produce more compression than if you're at that joint angle in a concentric contraction, if that's making sense. So really what you want to do with anybody in that situation is just limit the range of motion. So don't get to 60 degrees. If you're doing lunges, you don't have to do a full lunge. Yes, they're not doing as much work if they're not covering as much distance. So how do I get the same amount of work? I either increase the load or I do more repetitions or I work for a longer time so that even though I'm not going through the same range of motion, I can get an equal amount of work output by just doing more of it at a reduced range of motion that protects the knee, and I still get the benefit of the training.
Great. It's exactly where I wanted you to take me.
So it kind of went full circle back to the start of the conversation.
Yeah. The so another example, the adductor mangus, the inner thigh. Let's say it's a depth limiter, and most trainers never thought of the inner thigh in a lunge, right? Um, what does the adductor mangus do to the pelvis at the bottom of the movement, and how does that change the load on the lumbar spine?
So what happens as you get, well, so first of all, the when you're going into hip flexion and knee flexion, so those adductor and abductor muscles, the abductors actually are going to be put on some degree of stretch, whereas that adductor magnus is going to be relaxing a little bit. So what you're getting is an imbalance across that plane, and training the adductors to work along with the abductors to maintain a balanced state in that plane, which would be the transverse plane when you're in the lowered position. That's important. So what will happen, and it happens a lot with not just the adductor magnus, but even pectineus, which is this tiny little adductor muscle in the groin. When it's put in a disadvantageous position, biomechanically inefficient position, and it's forced to kind of hold and stabilize the limb, that's when those things get pulled. So those are things that are really worth working on. Especially if you're an athlete, working the whole adductor group is important. The thing, though, is the range of motion is less, right? They get stretched out pretty easily. And again, a muscle like pectineus, which is really tiny and vulnerable, it's easy to pull that. And if anyone's ever pulled that thing, it's painful. So not something that we want to be doing haphazardly or, without giving it some good pre-thought.
Thank you. That's not really often discussed outside of athletic training rooms or when you're working on that muscle group and having an understanding in the relationship it has to the pelvis and to the spine. And you could see if that's a limiting factor, typically sometimes they will adjust to get that range of motion with their back. What I've noticed is if you could identify those limiting factors right to left, you can pretty much with a lunge, a lateral lunge to the left and a lateral lunge to the right, you could see those limiting factors in a real snapshot view because especially if they're asymmetrical to begin with. And I think it's just such a cool thing about the lunge that you could various planes of motion where you're actually going to execute that vector load, you could see true movement quality of the individual that you're going to work with. So let's talk about ground force reaction and the drive back to a starting position.
Yeah, so that and I think you started with this, like, what is the sequence?
Yeah,
And there's a basic tenet in human movement science that when segments move, the the following segment should not initiate motion until after the previous segment has reached its peak velocity. So there's a sequential application of segment motion. Right. So too often, if you put that out of sequence, it leaks, to your term. It leaks force, it leaks power, because you want to summate all of the movement, the velocities, the forces. They should be summated through the chain. So if you start too early, then you're going to leak out a lot of the potential force that you're generating. Coming out of the ground, it starts at the foot, contrary to some people thinking that everything starts with the core. You don't start a lunge, you don't initiate a jump from your core, you initiate it from the ground. So when you begin, your first application of force is through the foot, right? So the foot segment, then the shank starts to move, then the leg starts to move, the pelvis is going to do some motion, and then the trunk should move. So it should go from distal to proximal. That's how you generate force coming out of the ground. So whether you're walking, running, jumping, leaping, hopping, whatever the case may be, it's a distal to proximal sequence, and we don't want to disrupt that, right? We don't want to um, affect or alter that chain of events, because otherwise then we get a suboptimal outcome.
and that kind of pretty much brings it all together, right? How the sequential order and taking any type of lunge, um, the a valgus collapse, the knee, diving in inward. For a trainer who sees that, what's the mechanical chain that produces it, and how does a lunge expose that, and how does a bilateral squat mask it?
So with the lunge, there are different reasons for that potentially to arise. Like, one is you're getting pronation, right? Subtalar joint, so inversion. And if the foot's unstable, if the subtalar joint's unstable, and you get that inversion, that's going to cause rotation or adduction at the hip, right? Which is going to put a valgus stress on the knee. It could be that the hip external rotators are weak. So piriformis, quadratus femoris, if they're not strong, they can't control that adduction which is occurring. Because you understand, when you're doing that lunge and you're getting all the weight on that front leg, you have to manage the position of the center of mass. And if the center of mass isn't ideally located, now you've got these torques which are causing the joints to move. Typically, the leg's going to go into adduction, so you want your abductors and external rotators to be really strong. So it could be an external rotation problem. It could be a weakness in glute medius, which is, preventing stabilization of the limb when you're doing that. So those are three areas to look at. So, what I don't want people to think is they're watching somebody do this and all of a sudden their leg moves and they're like, oh, well, your glute med is weak. Not necessarily. You got to test it first, right? So test the strength of those muscles, test it bilaterally, see if there's a side-to-side difference. What if there's no strength difference bilaterally, but you're seeing differences in the movement sequence? Maybe it's just that people aren't managing, they don't have an effective strategy on one side versus the other side. So it could be the way they're thinking about the movement. So the first thing you have to solve for is, do they understand how to do this thing in the first place? Because if they don't understand how to position their weight, how to control the motion of their center of mass, if they don't understand how to do those things, you may see deficits in the movement. And if our first thought is, well, they got a problem that they don't have good flexibility in their plantar flexors, like, wait, don't go there yet. Make sure that they know what they're doing before you assess how well they do it.
Yeah, I think um, kind of this leads me to how I would love to wrap this up on is I think uh, any trainer, therapist, gym owner needs to identify that happens through assessment or screening. It's not necessarily just looking at normative metrics, but actually truly how the individual's moving. And if you could measure those outcomes, that's great. If it's through monitoring devices, through a camera, or through the professional's eye, the beholder is a little bit subjective, but there's still meaningful information there. What's one thing about how they load a cue or program for any type of body movement that we discussed today? What's a takeaway that they can, what's the most important thing that you feel like we talked about today that you wish that they would take away?
From a biomechanical perspective, especially as it relates to lower extremity and upper extremity gets there are a lot of other considerations, but for the legs and for whole body movement, the most important thing from my perspective is understanding the position of the center of mass and understanding how we control our our motions within the goal of moving that center of mass somewhere in space. That really is, in my opinion, the most important thing to do. And just to finish with a little anecdote, I remember years ago I had a conversation with a group fitness instructor at Equinox, who was a friend of mine, and she was saying, I'm trying to get my class to squat and I'm looking around the room and nobody's like, they're all doing different things and it's impossible. I can't get them to do it. And I said, all right, so give them this instruction. Just tell them at the bottom, make sure that they can feel the weight, their body weight over the insteps of their feet, and then just push straight down into the ground. And she said, that's ridiculous. They need instruction. I said, no, just do it. Just get the weight over their insteps and push straight down into the ground from the bottom. She came to me like a week later. She said, I can't believe what happened in the class. She said, everybody was squatting right. I'm like, yeah, because you're not trying to teach them how to do it, which we mostly do incorrectly.
We
We're
overview.
give we over cue them, we over instruct them, we give them far too much information to process. All you need to do is get them to understand how to control the position of their center of mass. By telling them to put it over their insteps, they got to figure out where all the body parts go, right? That's what's going to do it. As you shift body parts around, it shifts your center of mass around. If you get it right over your insteps, that means you're aligning your body parts. Now just push down into the ground and it all moves straight up. And she couldn't believe it. But that's a key construct, whether it's squats, step ups, unilateral squats, lunges, wherever it is. Know where your center of mass is and know where you want it to go, and then create forces to move it that way.
Yeah, I would say my key takeaway is understanding it's the same, but understanding the loading sequence effectively so um, to under what's good and what's bad, right? Like
Mm-hmm.
this is a good way. You should be coming up all the way up off the ground. Uh, that sequentially is I can't stress it more than anything. And then measuring something that you can baseline throughout your work. You don't have to measure you could just go with intent for 90% of 95% of everything that you're programming. The intent to move as fast and as powerful. That's acceptable to me. You don't need technology, but to be able to measure on a movement power, look at eccentric movement, looking at concentric movement, is meaningful because you can baseline that throughout your life. And I just feel like that's where the directions are going with wearables today, where you could actually take that in. So if we could measure power over sets and reps, because otherwise rep counting doesn't really mean anything. To identify that work outcome is really what I hope people take away. So,
Awesome.
yeah, I really appreciate it. This was great. I look forward to our next one.
Yeah, me too.